Geometric dimensioning and tolerancing, GD&T, is a kind of a language used by design engineers to communicate the requirements on technical drawings. How about I tell you all about GD&T in a few minutes? Welcome to Exceedify. Our most important component is the feature control frame. It consists of 2 or 3 fields and an arrow. The arrow is also called the leader. In the first field, we put the symbol of the specification like straightness, flatness or parallelism. In the second field, we put the value of tolerance. This is the accepted deviation that we want to allow or tolerate. In the third field, which is not always required, we put the datum, which is the reference to which the specification is tolerated. Say we want to tolerate this surface to be parallel to that one. Then we have to give it a name. Let's say A. And we put A in the third field. If it was English, for example, it would sound like this. This surface should be parallel to that surface with a value of 0.2. Of course, we don't need to put a datum for every specification. If we want to say that that surface should be flat, then we cannot reference it to any datum. All it has to be is flat, not with reference to any other feature. So a specification like this would read out, the surface which is pointed at by the leader should be perpendicular to surface A within a value of 0.1. But what does perpendicular with a value of 0.1 mean? How do we evaluate that? To answer this, let's look at the different types of specifications that we have. We've got 4 families of specifications. Form tolerances, which include straightness, flatness, circularity, cylindricity, and profile. Orientation tolerances, which include parallelism, perpendicularity, and angularity. Location tolerances include position, concentricity, and in some cases profile. Runout tolerances, which are mainly used to tolerate rotating elements. These are kind of combined specifications that combine other specs like circularity, straightness, cylindricity, and concentricity in one tolerance. Normally, the specification would mean that the tolerated feature should either lie between 2 theoretical features with a distance between them, being the value of the tolerance zone. Or the feature should lie inside a cylinder or a circle with a diameter equal to the value of the tolerance. I'll explain what I mean. Let's zoom into each tolerance. Straightness. The tolerated line should lie between 2 parallel lines. The distance between these 2 lines is the tolerance value. Flatness. The tolerated surface should lie between 2 parallel surfaces. The distance between them is the value of the tolerance zone. Circularity. The tolerated circles should lie between 2 theoretical circles. The distance between them is the value of the tolerance value. Cylindricity. Same as circularity, except that instead of 2 circles, 2 cylinders define the tolerance zone. If the tolerated feature is neither a circle nor a line nor a flat plane, then we can use profile tolerance so that the tolerated feature should lie between 2 offset shapes. Each has the same shape as the tolerated profile itself, but has an offset between them with the tolerance value. Parallelism, perpendicularity, and angularity need a datum. So the tolerated feature should lie between 2 parallel theoretical planes. The distance between them is the tolerance value, and these theoretical planes are either parallel, perpendicular, or have a certain angle to the given datum. Position specifies that the tolerated feature should lie in a tolerance zone which has a certain location in the part with respect to other features. Position needs a datum and theoretical dimensions. So this specification means that the tolerated centerline of the hole should lie inside a tolerance zone, which is a circle with diameter of 0.1. The position of the centerline of this circle lies in a distance of 10 to datum A and 10 to datum B. Concentricity, or coaxiality, indicates that the centerline of the tolerated circle lies in a tolerance zone, which is a circle with a diameter of the tolerance value. This circle has the same centerline as the datum. Circular runout tolerance is used on rotating elements that are rotating around a bearing section. For example, if this part is rotating around cylinder A, and there is a gear that will be mounted on the smaller cylinder, then using the runout tolerance to tolerate this part is ideal. The runout simulates the rotary motion of the part already during the measurement. The part should be rotated around datum A. A measurement gauge is pressed to the surface of the tolerated cylinder and the gauge reading is set to 0. By rotating the part, the gauge indicates if there is a difference in height between the different points on the rotated circumference. This difference in height is the value of the runout. Okay, so now how would you read this specification out loud? It reads, the feature pointed at by the leader should lie between two parallel planes that are ideally perpendicular to datum A, and the distance between them is 0.1. Great! Now you started to speak GD&T.
If you found this video helpful, don't forget to give it a like and drop a comment below. We'd love to hear your thoughts or questions. And if you're into leveling up your skills with expert-led content, hit that subscribe button and turn on notifications. For full courses, downloadable assignments, and certifications, head over to excetify.com. Start learning smarter today.